Hello, and thank you for joining my lecture regarding image formation on the course of optics. So what I will be speaking about to my favorite student, and you are, of course, because you don't ask questions in my lectures. So what I will be speaking to you is that I will try my best to generalize our earlier treatment of forming an image out of our object point, and so far our object point has been relying on the optical axis. And this is of course somewhat boring example because that doesn't really tell us how an image would be conveyed if we would really have object points out away from the optical axis. So what we will do next is that I will allow the object point to be not on the optical axis, and let's see what we get out. And during this derivation, basically we need to look into three different kind of rays. So they are called chief rays. And once we understand how these three different main rays propagate through our lens, then we understand how the lens acts as an imaging component. And needless to say, we are here relying again on the paraxial approximation. So don't worry. That is always like under the hood. We don't implicitly mention it that much, but of course it's always there in case you're not sure. And I will already spoil some of the fun for revelations that the earlier divide lens equation that we derived for an object point relying on the optical axis, that lens equation still works for an off-axis object points. And this is nice because lens equation actually is a very neat, easy equation to use and understand how image formation works out. And basically, on top of that, we just need to introduce other parameters to describe the situation. And there I would like to highlight mainly the image magnification, transverse magnification, and longitudinal magnification. Out of these two, transverse magnification is by far the more important in the kind of framework we have in this course. So please pay attention when I will be speaking about that, because that allows us as a parameter to understand, for example, how we can form a magnified image. And that, for example, helps us understand how a microscope works and how telescope works, magnifying glasses work, and all these things. And if you look at the kind of upcoming lectures that we have, then it's needless to say that the transverse magnification will play a role in the future lectures that we have. And then, of course, like another spoiler alert, it is that the sign of the transverse magnification also tells about the type of a image. So mainly, is it an upright image or upside down? And why do we care? Well, for example, if you look at stars, we don't really care which way the star is like facing in the image. If you're looking at the eye, that's fine for us. But if you, for example, would be using binoculars or telescopes, then it would be a little bit cumbersome if you would see our object of interest, the bird in the forest, facing upside down. So those are the kind of considerations we might need to think about when we are really applying these, what we will learn in real applications and real context, so to speak. Okay, so this is what I will be speaking about during this lecture, and let's now get started. I will try my best, like making everything clear as usual, and I will start by just saying what we are doing, basically repeating what I just said. Now our point is to generalize the treatment and allow an object point to be actually not on the optical axis. And subsequently, of course, the image point will not be at the optical axis. Now this is nice because this really helps us to understand image formation, because then we can actually look how several object points are being imaged. So this essentially just means a image formation process. And that is what we would do in a real, for example, ray tracing software to understand how an image will be formed out of our like a lens system or imaging system. Now let's consider that if we have real lenses, many things of course will affect the image formation. And here the needless to say parameters will be the object location, SO, and of course amount of collected light will affect, so how bright or how dark our image will be. If you have ever taken a picture with a camera, and I'm sure you have, then you know that it really matters. Are we taking pictures in sunlight conditions or are we in a dark room? So really the amount of collected light actually matters on the image quality. Here, type of the lens also matters. So is it a biconvex lens? Is it a planoconvex lens? And is it actually a lens consisting of many different materials? So is it like a triplet lens? So essentially a lens consisting of 3 lenses and so forth. So these are the kind of considerations that in practice do matter into the image formation process. And how they matter is essentially beyond our scope. Here we are relying on the paraxial approximation. We do not have anything mathematical that can be used to understand optical aberrations. So how the lenses, different shapes of lenses would, for example, behave slightly differently. And we don't really consider that much about the kind of amount of light collected, so that how bright or dark or grainy our image will be. So these will be kind of some things that we will be considering in the follow-up courses. So this is our scope right now. And like I already said, paraxial approximation rules, and we will again apply this to our situation. And this means that we are basically only considering rays that are propagating mostly along the optical axis of our optical instrument, here a single lens. And that means that the angle phi, the optical ray that propagating through the system with respect to the optical axis makes, this angle is small, and then we can Taylor approximate, like they make a Taylor's expansion of sines and cosines, and then we see that the sine of theta, a small angle, is basically the angle in itself, and similarly for a cosine, what we get out is approximately a unity. And then, of course, if we would be in a real setting and we would be really considering a kind of real lenses, like this cannot hold in practice like rigorously all the time. And when it does not hold, then it would give rise to imaging aberrations. And mathematically, I already said of this in the previous lecture, like this is basically a result of a Taylor's expansion. We would just have a follow-up expansion terms here, and we would continue doing our math as we have been doing, and then we would be actually seeing the aberrations. So in a way, imaging aberrations and lens aberrations, there are the kind of second approximation into this description that we are using here. So beyond the paraxial approximation, we go and then we actually see aberrations and the different kinds of aberrations that exist. But that's a slightly cumbersome topic, or not cumbersome topic, but there's actually a lot of math involved because different kinds of imaging aberrations can exist. So let's leave that like into the follow-up courses. Now, as I promised, we will be looking at the behavior of an ideal lens. And here the incident angle doesn't really affect the behavior of the ray. So this is essentially what working under the paraxial approximation means. And in this case, it will be enough that we consider 3 so-called sheaf rays. And this has been highlighted in the figure A to C. So these are the 3 rays of interest for us. So let's look at the figure A first. So we are considering a ray propagating along the optical axis. So basically our object point would be at the infinity. That would be one way of figuring out where the ray actually goes, because that would allow us to calculate where will be the back focal plane. But essentially here we are considering now a ray propagating along the optical axis. So our object point is somewhere here, and then a ray continues a straight path, is being focused down due to a presence of a lens, and then it's being hitting the back focal plane here at this point, and of course it would be propagating forward afterwards. So this is something we would consider as the first sheaf ray. So it's propagating through the back focal plane Fi. Please remember this one. Then we look at the B figure. So there is another ray propagating through the system, and now it's propagating through the front focal plane Fo. And of course, with this definition, it propagates straight along the axis after the lens. So perfectly collimated ray of light propagating along the same direction as the optical axis afterwards. So this is exactly how we were defining, how we were finding the front focal plane in the first place in the previous lecture. And of course, we know that now we are actually seeing a ray propagating through. And then eventually it will be hitting our image point, since there will be no deviation from the optical axis. So we know already that the image plane will be somehow along this line here. We do not know how far it is from the lens, but at least we know how far it is from the optical axis. And then the third ray we need to consider is a ray propagating through the optical center O of our lens. And then what happens for this ray is that it doesn't refract here. Of course, in reality, it would be, and this is of course beyond our scope. Please join me in the next course, and there we will be considering, for example, thick lenses, and then we will be considering what would actually happen. So of course, in reality, the ray would be refracting here on the first interface, and then it would be propagating straight through into the second interface, and then it would refract again, and then continue with the same direction. But here we are considering thin lenses. We can approximate that everything that only happens takes place at the so-called principal plane of our lens, marked here with the dotted line or dashed line. And then basically our third ray propagates through the principal plane at the optical center denoted here O. So that's the cross-section of the optical axis and the principal plane of my lens. And here the same thing, like I haven't, I guess, explained what's happening here. I'm simplifying our drawing. So instead of making the ray bend slightly at the first interface of air glass and then at the glass air interface, instead I'm only drawing refraction process taking place inside the glass at the so-called principal plane. And of course, physically we do know that this is not how light actually works out, but this is how we do in fact draw these schematic drawings. And it's the same thing in here. Of course, in reality, the ray would be refracting here, propagating straight through the homogeneous medium. So of course, nothing magical would happen here, and then would be refracting here. But we just approximate things that this is in fact what seemingly seems to happen. So it doesn't really happen like this, but it's a convenient way for us to draw things and understand things. So these three rays of interest are the ones that we need to look at. And once we look how they propagate through the system, then we know how an image will be formed out of an object point that we know of. So let's draw these three chief rays into a figure. And now we have an object point at a given location, at a given height YO from optical axis, as has been shown in the figure here. So this is what we are now considering. And I have drawn the three chief rays into the picture, basically, to show what happens. And I will already spoil part of the fun here, so that this will be my image point at a distance of yi from the optical axis. And basically, where the image will be formed, it will be at the location where these three rays, or just two rays of them, will be coinciding. So that's where we will have our image location. And it's a nice thing because we can actually draw these figures, like these rays, quite easily once we know where we have the front focal plane and the back focal plane. And then we can actually just graphically understand where the image will be formed once we have drawn these kind of figures. And this is super neat because we don't really need to calculate much, and we don't need to use computers, but rather we can just draw things on a piece of pen and paper, and then we can understand how image will be formed. And hey, let's now look at the geometry more carefully so that we can actually derive some equations. And what we see by just looking at the figure, this is just basically some trigonometry. We can look at the ratio of the separations of the object point from the optical axis. So basically the distance of this our object point from the optical axis, we divide that with the modulus of our distance of our image point from the optical axis. This is essentially the ratio of focal length f divided with the SI minus f. And let's see if I can explain to you where we get this. So I'm just looking at the triangles here. So I have my SI minus f here. So that will be SI is the distance of my image from the principal plane of the lens. So basically from this dashed line. And then I'm subtracting f, the focal length here. So what I have here is essentially xi. So I could imagine that I'm looking at a triangle here, so that we have the height of the triangle is yi here, and then the side will be xi. And then I can look at the tangent of that, so that then I can see that this is essentially the tangent of some angle here. And then I will have this y0 divided by yo divided by yi. So I have this here, and I have my another angle I have this as an, hey, okay, this will be better. So I can imagine that I have a triangle here, and then I have a tangent of the same angle, and then the tangent will be essentially YO divided by F. So I'm moving this F into the other side and this Y into the other side, and then I see that I have YO divided by F here, and this is equal to tangent of this angle. Let's call this alpha, and then I have something similar here, and then I have the same angle here, but I have the different length, and I have the different height here. So then I have my yi here, and on here I have xi. So that's where I get it. So the equality of these two angles here by just imagining that we have two triangles here that look of the same form. This is tricky stuff, but basically it's just geometry, so nothing complicated in the end. So let's now consider another equality, and again this we get from the looking at the figure. So we have the ratio of the object location with respect to the principal plane SO, and then we have the image location SI with respect to the principal plane. So SO and SI are the distances here, and their ratio equals to the ratio of the sizes or distances of my object point from the optical axis versus the distance of my image point from the optical axis. So here again, what I should be looking at, maybe I should be drawing a triangle here. So I have my side length SO, and then I have my height YO here, and then I have my angle subsequently here. And then I would have my another angle here as in the height YI, and then I have the side length SI, and then I have another angle, and I would guess that that would give me another triangle, and I'm now wondering that can we understand their ratios here. I would guess so that's how it works out. So we have alpha. So we have SO, YO versus SO, and then we have equal to YI versus SI. So YO divided by SO, it's essentially this one. So I have my tangent of this angle, and then that should be equal to the tangent in here. So these angles should be the same, and they will of course be by just looking at the geometry. So this is a line parallel to the optical axis, and this is the same line here. So definitely this is also parallel to the optical axis. So I know that this angle here with respect to these two rays equals to this angle here, and then by just looking at the trigonometry tangents of that alpha, I can verify that this is the equality that holds. Intimidating to kind of see, can I hand wave the final ladder equalities here? And trigonometry is hard. I can give you that. At least it's hard to me. So then we have the final ratio, final equality. So we have XO divided by F. So let's look at this. We have XO here, and XO is our distance of our object point along the optical axis with respect to the front focal plane. And of course, XI is the same thing here, but it's the distance from my image plane with respect to the optical axis from the back focal plane, FI. So here I have ratio of XO versus F. So I have this and I have this. Okay, this looks complicated. I'm wondering what I should be considering here. What would happen if I would have if I would take this and I would divide that on the other side? I would have XO versus YO. So I would have this XO versus YO. So I would basically have a cosine of this angle, and then I could take what it would be a cosine of this angle. they will be the same. So because this is a line going through, and then this side length will be f, and this will be y, so yi. So that explains this angle. So essentially I'm looking at this triangle here and this triangle here, and the fact that this angle here would be equal to this. So then with the cosine of that angle, I can equate and find a relation between the xo versus f, that it must be equal to yo divided by yi. And then the final thing, I guess I do not go forward anymore. This must be the same thing here, but I'm just looking now at the two different triangles as before. So I'm looking at this triangle drawn here from the back focal plane, and then from the back focal plane towards the lens. And then this angle here must be the same as this angle, and then I can find out the equality that f divided by xi must be equal to the ratio of yo and yi. So yes, I was a little bit worried that can I explain this equality, but I was able to, and this is super cool because this actually gives us a lot of equations that we can use in what follows. So this we can, for example, use to find out what is the transverse magnification. We can use that to derive Newton's formula, so basically a kind of lens equation that was used before, and we can also solve this to find a lens equation. And verify that lens equation also works for this object point that is not on the optical axis. So I do not show this derivation, it's trivial. You can just take the equalities that we have the ratio of SOs and SIs with respect to the focal lengths. So we take the kind of middle equality, and we can verify that the lens equation 1 over SO plus 1 over SI equals to the inverse of the focal length. And if you are familiar with this, please remember inverse of the focal length is equals to d, the lens power. So sometimes that is a useful thing to kind of understand when we are looking at the kind of behavior of lenses and their imaging qualities. So this means now that the equation holds also when the object is not along the optical axis. And this is nice so that we can really see that this kind of figure actually works out, and we can understand how the image gets formed. So please, in case you haven't drawn this kind of figures at the high school, during my time we were actually drawing a lot of these kind of figures at the high school, and maybe in the upper elementary now you're doing that. And if you haven't drawn these kind of figures yourself, maybe you should draw a few to kind of get a good point of understanding. So basically you can just draw some lengths, and then you can assume that what will be the focal length. You draw the focal length on the equal sides, equal distances from your lens. And then after that, you can draw your object point somewhere, and then you can draw these three lines. It's quite easy. The one line just goes along the optical axis. It bends at the principal plane, and then you just draw a line that goes through the back focal plane and let it continue along in your piece of paper. Then you have the second line, and then you take your object point, and then you let the ray go straight through from the middle, the optical center of your lens, and then you just let that ray to propagate without any refraction through the system and through here. And then the final ray would be that you take a straight line and which you let to propagate through the front focal plane. You hit the principal plane of your lens. In the case of a thick lens, you would actually have two principal planes. That seems to be what I was thinking a second ago. So it hits the principal plane, and now you know this was the chief ray that you let then propagate along the optical axis afterwards, and then you will trace a path, and then at the location where all of these three rays intersect, you know that will be where the image will be formed. So you can really just graphically solve things once you are able to draw a lens, the object location, and the focal planes, so we're at the distance of f from the principal plane of the lens. So this is how it works out. And this relation, the lens equation, it's nice, but we can also find another equation that tells us something about the image formation, and this would be taking the latter equality in the last slide's equality. So then we can multiply xo with xi, and this must be equal to f squared. So this is basically just the latter equality, rearranging the terms, and this equation is known as the Newton's formula. Why do we care? Well, this is sometimes it tells us quite a bit about the kind of what the xo and xi should be with respect to each other, because we know that on the right hand side we have a positive number f squared, and the focal plane, so for a focal point, focal length should be a like normal real number. We don't have any kind of complex lenses here. I don't know how they would look like. And then essentially this xo multiplied with xi, we know that this should be also a positive number. So basically, like if we would have xo between the lens and the first focal plane, then we would know that the xi should be also a negative quantity, because otherwise, like this equality would not be able to hold, because we would have a negative number on the other side, on the left-hand side, and then we would have still a positive number on the right-hand side. So this already kind of tells us that if you happen to have an object here between, then in a way we're not in trouble, but at least we know that then the xi subsequently will also be a negative number, so that then never we will have an image formed somewhere like behind after the back focal plane of my lens. And on the similar way, we see that if xo is positive, then xi must be a positive. So for example, in this case, we see that the xo is positive, then xi must also be positive. And please remember, like, what is the difference between SO and XO? So SO is the total distance from the object into the principal plane of the lens, and then XO is the distance, the length between the object point and the first focal plane. And now let's look more finally into the kind of magnification. So when we are more like imaging objects, of course, many times you actually want to get a given magnified image. So for example, a kind of prime example would be a microscope, where the kind of main function of the microscope is that we want to form a very highly magnified image of something small, so that we can actually inspect that with our eyes or with a camera and see what happens there. And this historically was a kind of very big thing optically, that people are figuring out that there's actually something kind of like small things living inside many things. And that's how, for example, bacteria, viruses were found, and kind of information was gathered biologically that they kind of everything seems to be consisting of cells and whatnot. So from the kind of historical point of view, optical microscopes have played a huge role in the advancement of information and understanding of mankind. So this is one example. Magnifying lens would be another one, telescopes would be another one, and so forth. So many times we want to kind of fool around with the magnification of my optical imaging system. So let's define something, and let's define a transverse magnification, MT, as a kind of quantity of interest. And let's just define this MT, transverse magnification, to be that it's the ratio of the kind of sizes of my image. So essentially, like if I'm looking at the kind of furthest of object point, and that would be denoted with the YO, then I want to get a given magnification. So I want to see that then the image that will be formed will be, like, for example, slightly larger. I see that I have a magnification MT that is larger than unity. If the object and the image are of the same size, then I have a unity here, and then I have my transverse magnification equal to unity. So this seems to be like a nice way of defining my transverse magnification. And from the previous slides, equalities, we can also write another ratios for the transverse magnification. So that can be also written, please note the sign here, as a minus of SI versus SO. So the kind of separation, the lengths, distances between the object point from the principal plane of the lens and the image point from the principal plane of the lens. And here, let me tell you already here that for example, in the previous slide, we had a figure where SO and SI were both positive numbers. And please note here, I have a minus sign here, so that I seem to be having a kind of minus sign transverse magnification. What this sign of the transverse magnification actually tells us, it tells us, is the image upright or is it upside down? And in the usual case, and maybe you should go back to the previous slide to kind of verify it yourself, the kind of arrow we draw from the optical axis into the object point, that was pointing upwards. So that would be my kind of like normal looking figure and or image. And then when I'm actually imaging that with a positive convex lens, I'm getting an upright image. So that the arrow that was pointing towards the point YI, that was actually facing the other way around, and the arrow at the object plane. And this is what the minus sign here just tells us. It might be that the arrow is longer, but it's just pointing at the different direction, so that the image that will be formed is actually upright, upside down. That's what I want to say here. So please note that the sign actually matters, and sometimes that's actually a very important thing to remember, because it might be the case that we want to have a kind of normal image, upright image to be formed. Arg, something will be happening to my Outlook. Let's see if you can hide that. So let's proceed. So now another equality, and this is again follows from the trigonometry of things. So I can also write that the transverse magnification mt equals to minus xi versus f. So this is also what works, and this is just basically looking at the previous equalities. So this is what follows from there, and please note the minus sign here again. And similarly, we can write the magnification with respect to the f and xo. And please note here sign conventions of the parameters. We should remember them, and of course we should understand physically what it means. If we have a positive transverse magnification, then the image will be the same way as our object. And then if we have a negative transverse magnification, then it will be upside down. But then nevertheless, like if, for example, transverse magnification is -5, the image will be larger 5 times than my original object image. So like that's what the negative sign doesn't mean. It doesn't mean that somehow it would be shrunken down. Only when we have the magnification smaller than unity, then the image will be smaller. And we can also define a longitudinal magnification, and this is maybe not the most interesting most of the time, but if you would be, for example, doing optical microscopy with a very high numerical aperture lenses, so very powerful lenses, then sometimes this will be also of great interest, so that how much things will be shrunken down or magnified also with respect to the longitudinal direction. And this we define that it's essentially the derivative of my xi parameter with respect to the xo. And let me show this. What that means, I have a figure, but basically I will go through this first and explain later. So I have a figure here, yes, finally, that tells us what I'm wanting to explain to you. So transverse magnification tells us how much further off my image point is from the optical axis as my object point. And then similarly, like the longitudinal magnification, we can define that now instead of like at the original location point, what if my object is actually a 3-dimensional object? And then I would need to also consider what happens for a point that is not at the same distance as the original object point and slightly off. And then I can draw a triangle here and consider that this small deviation from the original plane of interest is total differential of xo. And then similarly, when an image will be formed, there will be a similar shift now towards the lens, and then the shift will be total differential of xi. So essentially with their ratio, I can then define that how much my imaging instrument will be magnifying things with respect to the longitudinal direction, so basically along the optical axis. And these magnifications, I can plug in my equality for the xi, so that was basically equal to the f squared divided by xo. So basically I'm taking this, I'm taking f to the other side, so that's what I have. And then I can calculate the derivative. Sorry, I'm missing the the minus signs cancel out, I'm not missing anything here. And then I can calculate these things out, so I get this kind of equation for the longitudinal magnification. And then I can equate that this is actually the square of my transverse magnification plus the minus sign. So I can see that once I magnify, once I get a system that is strongly magnifying things on the transverse direction. So for example, I would have like, I don't know, transverse magnification of let's say 100, then I would see that the longitudinal magnification will be even more. So that this is something that we learn by looking at this. But here, most of the time in our case, we're not interested in longitudinal magnification, but it starts to be more important when we are having more powerful lenses. And then, for example, if you do photography, maybe you're familiar with the bokeh effect, essentially that you take a picture out of some object, and then only the object is sharp, and then the background is blurry, and the front of the figure, the front of the object is blurry. So that's where essentially we're seeing this longitudinal magnification to play rise. So basically something is actually happening in terms of the image formation processes when we're kind of looking at objects that are not at the same plane anymore. So we're looking at three-dimensional objects or sceneries essentially, because when we were thinking of a scenery, it's a very, very three-dimensional object we're actually imaging with the camera. But this is what I wanted to say. And finally, want to kind of conclude that there's these sign conventions, and we should be very careful when you're trying to understand what happens for the image process, for image formation process. So for example, like if you have this distance of my object point from the principal plane of the lens, if it's positive, then the direction from the lens is on the left hand side, negative, it's on the right hand side. And this is more important when we're actually in the future looking at many lenses, how they are being forming images. And then like if we have a positive SO, then we have a real image. If it's negative, then we have a virtual image. And the same thing for the SI. If it's positive, then it's on the right side of the lens. If it's negative, then it's on the left hand side of the image. And then the type of the object, is it real or like virtual? Then YO, if it's positive, then it's above the optical axis. If it's negative, then it's below. And then the YI, if it's positive, then it's above. If it's negative, then it's below. And with these sign conventions, then you can, for example, make sense that when we have a positive transverse magnification, then the image will be upright. If the transverse magnification is negative, then it will be upside down, and so forth. And sometimes it's actually also important to kind of realize, do we have a real image or do we have a virtual image? So in a real image, the rays, the chief rays are actually coinciding. They are really propagating there into that point, forming a real image. And if it's a virtual image, then we are kind of drawing the continuations of those chief rays. And then we kind of see that it seems to be that the rays are converging somewhere. But we will get there on these kind of description slightly later at the end, especially when they're doing homework, that what is the difference between the real image and a virtual image, and maybe in the discussions afterwards. But I thank you for your patience. Like this was a little bit long lecture, but I hope that it was worth it, because we now kind of understand how a thin lens will be forming an image, and especially like for the case that the object point is not at the optical axis anymore. And after this, now we are kind of going bravely into the combination of lenses. So we are now like putting many lenses in a line, and then we want to understand how we can understand image formation processes out of this kind of more complicated setting. So basically how we can start understanding propagation of light and image formation in optical instrumentation. But that, of course, will be the story of the next lecture. So I thank you for your time, and please enjoy the rest of the day. Thanks and bye-bye.